Hello, hello. This is Postgres FM episode number 70. My name is Nikolai, and together with me is Michael. Michael, hello.
Hello, Nikolai.
So, what do you think we should discuss today?
Well, this week was your choice, right? I think you've picked a nice topic that was a listener suggestion. So I think we've simplified it to data model trade-offs. Is that
Right,
fair? A
or
fair summary?
right, or how many? Purely relational. Let's emphasize that we are going probably to keep JSON columns as a separate topic. We had it already,
Yeah.
but
Let's.
question.
Well,
Let's.
they specified they specified with respect to PostgreSQL internals almost as a.
Internals. Okay.
So that's quite a nice way of looking at it. It's what could come up as a result of Postgres specific implementation details that should
All
make
right.
us consider data model decisions.
All right. So Postgres allows a lot of columns to be present in a single table. How many?
A
256?
lot,
No,
yeah. I'm not actually sure. I think it's
maybe
more.
more. There is some limit.
Yeah.
Oh, okay. Poor preparation. You should prepare better. Okay. Anyway, you can have hundreds of columns in a single table, and you can have indexes on those columns, or you can go and implement Boy's code normal form, right? And so on. And there are many directions to move. And of course, everyone wants very good performance and compact storage and so on. Is it so? Maybe not everyone.
Well, I think most people care about performance on some level, but I think it's easy to list three or four things that almost everybody cares about more, like durability, for example, or everything in ACID. you know, there's a reason that people pick Postgres and pick old databases and trust old databases more than some of the newer ones is because they care about things more than performance. I think I would argue that anyway.
Well, right. But if the question is related to internals, I guess we should think about performance first of all, and performance in terms of various aspects of it, like read time, write time, um, various overhead we can have. And so to me, if we simplify the question a lot, it's a question how wide should be our table, how many columns we should afford, or should we normalize versus denormalize, or should we have a lot of columns in one table or fewer columns and more joins when needed. It's not directly the same questions actually, right? Because of course sometimes, of course, denormalization is when it's done on purpose, like intentionally. It means that we extend the same table, putting more columns there, although those columns should be somewhere else, for example. But sometimes it's very different things, and if we just follow like normal theoretical approach, normalizing our model, we can easily end up having a lot of columns in a single table, a lot of them. Because usually, if you think about some social media application or some mobile application, usually if it's a big project, growing project, we have some entities which are like central to our model. For example, users table, how you can call it, person. Or for example, if you have kind of organizations or projects or something, these tables are going to be central. A lot of other tables will have a foreign key pointing to this central table. And eventually this central table is going to grow in terms of width. You will add more and more columns because you need to track something. Sometimes just because of denormalization to avoid extra join and maybe aggregates, like count, right? Sometimes just because the complexity grows and you just need to keep more properties, and each property in a pure relational approach, it's just a single column, new property, new column, right? Attribute, field,
So what's? I mean, I
semantics.
think the the obvious question is, why is that a problem? Why is a wide table a problem?
Good question. Well, there are strong trade-offs here. On one hand, extending in terms of width our table is not a problem. We know how to do it with zero downtime very nicely. Postgres 11 brought us default for existing rows without virtual default, I call it. It's not official name, but this is actually what happens. Instead of rewriting whole table, when you add a column with default, it's stored virtually for all old records, right? And you just your alter is very fast. So we know how to deploy changes with zero downtime, with proper testing, all good. Then we create indexes with create index concurrently, because obviously more columns means more indexes, because some columns you want to be present in indexes because you filter, order, and so on. But trade-off is, on one hand, it's good to have a lot of things in one table because you can achieve single index scan or single index only scan for many queries. Because if you need to join data from multiple tables, you cannot have single index scan.
You can't have a single scan, full stop.
Yeah, because index cannot be defined on multiple tables, and the only way to do it is to define materialized view and deal with all issues it brings, because it will be it will need maintenance and proper use. So if you have multiple tables, let's consider a simple example, one-on-one relationship. Somehow you ended up having, like, for example, users table and users extra properties, for example, table, and somehow you decided it. And it's maybe not a good idea, because you cannot, for example, filter or order by just with index scan using columns from both tables. For example, you want to search by email, lowercase, or case insensitive CI text data type. And at the same time, you want to use some extra field in this search or order by it. And in this case, Postgres will need to choose one of three join algorithms and apply either nested loop or merge join, depending on, even if it's a mail, probably it will be nested loop or something like that, right? So it won't be looking super cool, because super cool is like index scan, index only scan. I'm not saying like joins are bad, because joins in Postgres quite optimized, three algorithms. In many cases, they work really well, but you cannot beat the performance of index, or in more important, index only scan, right? So to have that, you need to bring those columns in the main table, users, for example. And in this case, you can define a multi-column index, and your query will be super fast. You will have like just a few buffer hits to find those one or a few rows, and it will be below 1 millisecond for sure, right? And that's great.
Well,
that's it. End of story. Let's have
I don't
a lot
think
of
that's
columns.
it.
No. Sometimes I say, okay, sometimes even if we perform normalization like we learned from theory, at least to third normal form, very good situation already, and then I say, okay, maybe we should go back and denormalize just to have index only scan and avoid joins. But this is just one part of story. Another part of story, there are many issues you will have when you have a lot of columns and indexes, and this correlates a lot with previous episodes we had recently, over-indexing 2 weeks ago, right? Right.
I think, is there an even more fundamental problem? Almost by the design of Postgres, we store data as a row, like in tuples in pages, right? And because we're doing that, if we've got really wide rows, we can only we reduce the number of tuples per page that we can store. So as soon as we're accessing multiple, like we might get that index only scan, but if we're frequently only reading from a few, like a couple of those columns, and maybe they're really narrow columns, those being on a separate table to the wide ones that we're infrequently accessing is an argument against the wide table for read performance. So even if we only focus on read performance, I think there are some arguments to have splits like that.
Yeah, makes sense, right? But again, you can compare for your particular case. You can conduct a few experiments and compare exactly with explain analyze buffers. You will see how many buffers, how much IO each approach gives you. And I suspect for reads, not in all cases, but in many cases, for reads, wide single table will still be good. Even if it's toasted, right? If we exceed 2 kilobytes for a row, like roughly it will be toasted and so on. It means actually implicit join, right? Because to find those chunks, Postgres will need to perform. But buffer hits or reads will show this as well. The problem, the second part of this medal, second side of this medal of this coin is that extending the number of columns we have in the table, we have two big issues coming. They can come not in acute form. They can come slowly and increasing over time and accumulating this. So two problems. First problem is that how writes are working. How updates and how updates are working. Updates means an update in Postgres means that the whole tuple is copied, right? And this means that if we have a lot of columns which we, like you said, access not often, during update we need to copy them. This is first part of the first problem. Second part of the first problem is indexes. More columns usually means more indexes, because again, you need to work with indexes. You need some additional to work with columns. You need additional indexes, and if you update a row, it means, or if you insert a row, also it doesn't affect delete. But again, I had this mistake a few times. Delete doesn't matter, but inserts and updates, they will need to change all indexes you have. You have many columns, you have many indexes. To update just one column, you need to, or to insert a row, you need to update all these indexes. There is a heap-only tuple update optimization, but it doesn't work often. It doesn't work always. It requires two conditions to be met, and it's not always happening, right? So if we have a lot of columns, we need to write more. We need to update indexes often, and this makes our writes very heavy, right? And it gives a lot of work for AutoVacuum, for example. Simple example: if you decided to put a counter to avoid slow aggregates. For example, we talked about users. Okay, how many comments this user left in various places of our system, or how many posts this user created? I'm speaking in terms of some abstract social media application. If you put post count as a column to users table, you will need to update it quite often. And all columns will be copied always, and all indexes will need to be updated when this update is not hot, or if it's insert. But okay, here we talk only about updates. So if update is not hot, all indexes will be updated. It's called index write amplification. One of the reasons Uber decided to go back to MySQL. So what does it mean? It means that probably we need to think carefully. If this is a central table specifically, which will be used in many queries, And also, if it's a central table, it also will be often used as just single index scan just to find the current user, for example. Who is working? We need to find current user. Of course, you can cache it, but still, you need to find this user, right? And then you need to update it. So probably it's wise to keep this counter in a separate table, one-on-one relationship, like user extra data or something, and count is there, and it will be narrow table, only some numbers, and foreign key to the main table, and and unique also key to maintain this one-on-one relationship. Maybe it's primary key as well. So you just update this counter. Maybe there are some other counters or timestamps. Another example here is like last blah blah at, for example, last updated at, last commented at, last created some post at. Some timestamp, it's like usually 16 bytes timestamp with time zone or without. Usually you should prefer with timestamp, and it's 16 bytes. And keeping it separately and just having an extra join when needed, maybe it's a wise approach, because the main table remains untouched if you need to update it often, right? And the index write amplification is lower because only few indexes there, which probably just one index actually. You probably don't need to index those extra columns like counters and timestamps. Sometimes you do, of course, but in many cases you don't. And in this case, it's just one or a few indexes to be updated. Index write amplification is not high. It's not a big problem anymore.
Yeah. And we avoid a lot of bloat on the main table, right? Or a lot of additional work on the main table, as well as the write amplification. We also don't have to free up or reuse that space efficiently in the heap. Presumably there's an impact on the write ahead log, the amount of work we're doing in the write ahead log as well?
Well, yes. Yes, it is so, but we also have full page writes, right? So full page write means we need to write full page anyway, but for subsequent writes until next checkpoint, if you need to update very narrow table, tuples are small. In this case, of course, amount of data written to wall becomes smaller. So you're right; it's a good. Another good reason, right? So if we write less wall data, it means less pressure on backups and replication systems.
Yeah,
right.
Exactly.
But again, you need to join. So probably like we end up with like this approach. If this is something like counter or timestamp or something which is very often updated, but we don't need index on it, it's good to keep it in a separate table.
And one other condition, if it's not like highly correlated to something else, if we don't need statistics, like is it called multivariate statistics? If we don't need to define those, anything that's single, I guess all the single table features we have, this applies to as well.
Right.
Oh, and I thought of one other. I remember reading a really good blog post by Haki Benita on this topic. So we've got the frequently updated columns that we should consider, or that it might make sense to move out into a separate table. And we have these, large or medium-sized text. Now, large ones, more than I think you already mentioned, the 2 kilobyte number, Postgres already handles those for us using Toast. Awesome, but it kind of shows that there is a point where it becomes beneficial to do this join. We get some other features in there as well. But there's this weird case, like below 2 kilobytes, that there's an argument that medium-sized text you'd consider moving those out as well. If you've got comments or something that are like 1 kilobyte on average, having those in your pages means you're only going to have maximum 4, or what would it be, 8 tuples per page. Yeah, exactly. Tuples.
Four.
Keep saying that wrong.
Two. Well, I'm also switching back and forth. Tuples or tuples, 4. If it's pages 8 kilobytes, 2 kilobytes, like 4, roughly 4 per page. Yeah. So it's interesting point. Another interesting point is vice versa. If some column is like very rarely used, very rarely, but it needs index, then also probably it should go to this extra table. For example, token, activation token.
Interesting, yeah.
If you put activation token to users table, it's becoming like forever passenger, not doing useful work anymore at all. But you keep having it in all updates. You copy in all raw versions and tuples. Why?
And reads. And returning that data to the
and
client,
reads.
like every
It's
read
bloating,
as well.
bloating reads, and if you do need it one time, although it requires usually token requires index because you find raw, like using token, you find who this token belongs to, right? The owner of this token. So you need the index. But in this case, you need it to just like once per lifetime of user, or maybe when user resets password or something. It's so rarely. So keeping it in a separate table, even if it's with index, it's a good idea. And it compacts the storage and memory representation, less bytes used in shared buffers, because probably you do it once, then you forget about it and never read anymore to shared buffers until password reset is required one more time.
That's a really great point. I've got another question for you around.
It leads us to the second problem, but let's cover your question first, because second problem is also interesting.
This is so the question is, if you've got a really large, if you're like chucking some HTML into Postgres for some reasons, that makes sense for your use case in this case, and maybe it's potentially megabytes or something of data. Now we could rely on Toast for this, but we could proactively put it in a separate table and it would still use Toast, right? But to avoid it's almost the developer experience. If somebody's accidentally running select stars or isn't aware of the impact of fetching that data and does a select star, if you're having to support those kind of queries, not having them it'd be possible to have to fetch megabytes and megabytes of data from the server by mistake when they probably don't need it might be an interesting idea.
Oh, definitely. So definitely, if it's some project which was developed during many years, and if you look to these central tables, especially like users, like I said, or project organizations, and so on, they are used a lot, and of course, like if you can check Toast level with various queries, it's easy. And if they started to be toasted, of course, select all columns, including those which you don't actually need. Usually you need it often, but you need only few columns to check that this user is still active, right? No, like it's not, this user is not banned, for example, or project is still active, is visible. It's just a few most important columns which required often. Mm-hmm. Others can be offloaded. But again, there is a trade-off here. If they are offloaded, but with indexes, you need to join, and Postgres Planner choosing form of join and indexes, it will be sometimes less performant than just single index scan, right? So it's an art. When you build something, you need to predict future, and this comes with some experience. You need to think, okay, these columns, will we need them often? Will we need indexes on them? And based on the answers here, we can decide to offload them to this extra table, right? So the second problem is over-indexing. We discussed it. If you have a lot of columns, you have many indexes, you quite often have single index scan or index-only scan. This is the perfect plan you always want to see, because it's usually either sub-millisecond or few milliseconds only, depending on the number of rows and hardware. So if you have this, you start having a lot of indexes, and not only it's index write amplification problem, it's also the problem we discussed, exceeding 16, 15 indexes actually. Even if your query deals only with single table, but it has many indexes, if you don't have prepared statements used, planning each time, this planning will be slower and exceeding this number of locks, 16 table plus 15 indexes, already 16. 17th index locking will be with fast path false, so without fast path for lock manager, and it will be much slower than with fast path, and it means that you quite like if it's central table and QPS for queries involving this table, especially simple queries, they can be very high, very frequent queries, high QPS. In this case, contention for simple queries might hit performance a lot. So you will see lightweight lock manager in wait events in PGSet activity, or in on RDS performance insights. Cloud SQL has it as well. Timescale, I think, has it as well. Wait event analysis will show you waiting on lightweight lock manager. And this will happen with very simple queries, primary key lookups or some index scans, finding single row, just because you have a lot of indexes and query is very frequent. So offloading might help again. If you think, okay, this table is going to be central in my system, and these columns I do need. Most of them will be indexed, but I won't exceed this magic 16 number. I mean, for indexes, it's 15. And in this case, I will be able to have thousands, maybe dozens of thousands of queries per second to this table, because I need it, right? Not everyone needs such performance, of course, right? But designing for such performance means you need to avoid having more than 15 indexes per table. This should be a rule for high frequent tables, or you can just use prepare statements. It won't eliminate this problem completely, but it decreases it because you eliminate planning time for primary key lookups. Execution time might be even bigger than planning time, so you shave off a lot of milliseconds, microseconds from this duration, and contention also can happen, but at higher QPS. So you postpone this problem. If you do need to have more than 15 indexes, but having less indexes is good, because lock manager won't have contention if you deal only with single table.
And we can refer people to the over-indexing episode.
Over-indexing,
I've got a theoretical question around that, though. Not something I've ever seen become an issue as a result of this, but by splitting, if we follow this pattern in a few places in our database, and we've split table things that are logically one table into multiple, we're going to have more joins, and there's a couple of limits, planner limits. Is it from collapse limit and join collapse limit? And I think is it 8? Yeah, okay.
By default,
I knew it was and that we could quite quickly reach 8 relations if we join. So then, so you might, if you're doing this, you might also want to just check that any of your complex queries that involve a lot of joins don't flip plans, or you're not getting some strange. I think it switches to is it called the genetic query GQ genetic query optimizer?
Genetic query optimizer. Yeah, right. It's I'm checking 12. I always keep forgetting
12.
Genetic query optimizer threshold is 12. So if you have if you reach 12 relations, by the way, here we mean tables, not indexes, because previously we counted both tables and indexes when we talk about locking. Here we talk about tables, and yes, if you join 12 or more tables, it means that genetic query optimization starts happening. It's hard to understand this thing, how it works, right? And maybe you are good, maybe you are not. So I in general, I of course aim to have good performance, and joins are fine, but usually I try to avoid joining too many tables. And how to do it? Generalization. In this case, yes, we need wide tables. It's worth saying that what I just described it's about very high TPS, high QPS, right? So if you have hundreds of queries per second, good hardware, you probably will never see this log manager contention. But in this case, of course, generalization is one way to reduce the number of relations in participating in query. Another way, of course, sometimes we do it, sometimes we just, okay, we read something and then we read something in different query. It's also possible, but yeah. Or do you know, like if we use with materialized keyword, meaning we intentionally put optimization fence there, it means that these steps will be performed, like this threshold is considered separately, right? So if first step was 6 tables, second step is another 6 tables, plus previous results, of course.
I don't know what happens with join collapse limit there.
I think it's separately. These subqueries, even it's single statement, these subqueries physically it's separate thing, right?
By the way, you were right.
We have materialization step, right? And we just in memory we have like temporary tables, like so to speak. It's not a table, but just some data, right? It's used like a table.
Makes sense.
We can join with it, right? In this case, splitting to multiple steps using CTE might help as well. I guess. Like I see some overloaded in terms of number of tables used queries quite often, but usually we find like some ways to simplify them. Sometimes a lot of tables participate almost for nothing there. Like, it was like just convenience. Let's join this, let's join that. But then you ask like, why? If you want good performance, maybe you should just make it lighter, right? Not so heavy. In this case, you just reduce the number and it quickly becomes below 12, right? So, but I don't know, maybe genetic optimizer is a good thing. I think only few people in the world know exactly is it good or no. It's like some mystery, right?
Yeah, well, one thing to bear in mind is that unlike previous topics we've had, this is a configurable limit. You can change this number with the caveat that you to keep an eye on planning time. Basically, the reason these limits are in place.
And you can do it dynamically. You can change it for one query, change back before another query. Same with join from collapse limits. But it's not the same with thresholds I described, like with this fast path locking related. 16. It's hard-coded constant.
Is there anything else you want to cover? I've got one more thing on the denormalization front.
I wanted to mention that what I described, we have recent benchmarks. Thanks to my co-workers, especially Vitaly and Dmitry, they did good benchmarks, and let's put links to description. Very detailed. Everyone can repeat them as usual. We always, when we perform something, we describe all the steps, all the details, so it's fully reproducible. So these benchmarks show like the effect of having extra indexes, for example. Sure. And I actually, until recently, I never thought that having extra indexes is affecting planning time significantly, like 5%, 10% of overhead in terms of time. And I also never thought it's related to this topic, actually, we discussed today. More columns means more indexes. More indexes, faster we reach this 16 threshold. So it's interesting. I must admit it's new to me. This is what I want to say.
That's cool.
Yeah.
On the last question I had, the case I see most commonly for denormalization is around, like, for example, with a software as a service company wanting to partition a large table by account ID or your equivalent, you need to have that on the table in order to be able to do so, right? So like that's so it could be like a not only for read performance but also in preparation for something like partitioning.
Right, partition key propagation, right? We need to propagate this partitioning approach to like dependent tables. This is quite obvious, I think, right? And again, like if we partition, we need to make sure all our queries, or at least most of them, don't deal with more than one or just a couple of partitions. Otherwise, we can have another amplification. It's not index right amplification, but index planning time locking related amplification. Because if you have partitioning and your query deals with multiple partitions, each partition has, for example, 5 indexes. If you deal with 4 partitions, you already have 20 logs plus tables, so 24, right? Logs to be acquired, and it definitely goes above this threshold 16. So fastpath won't be there for some logs, and locking will be slow. So you do need prepare statements at least, or you need to just make sure consent exclusion is working, and your plans target just one or a couple of partitions always. Yeah. Better one, right? And that's it.
Of course. Awesome.
And if it join also. Oh, of course, if you join often, main table has many indexes, extra table has many indexes. When you just select from it, planner needs to lock all. At planning time, we also need to lock all of them actually, with the like lowest possible heavy lock, access share lock, just to avoid DDL to happen while we are reading. But all indexes, even those which not needed, will be locked. This is the key. We discussed it. So if you split to 2 tables, but need to join often, and this join query needs to be very frequent, it's worthless to split.
It's worse. We've actually added a relation. Yeah.
Right. Yeah, we added relation +1. Okay, and we also need to perform join now. So it's worse. So if you offload something, you need to be very careful. You need to columns which rarely used, or columns which need to be very frequently updated, columns which shouldn't be indexed, or indexed and rarely used. I guess there are some maybe design patterns here worth developing. What we discussed is kind of raw material. We need to polish it, I guess, before saying this is a recipe.
And the whole point of this episode was it's a trade-off, right? Like there are going to be cases where one of these makes sense, and there are going to be cases where the opposite makes sense.
Right. Right. Yeah, it's better if it's a serious system that will need to handle a lot of queries per second. It's worth checking, prototyping, filling with millions of rows, hundreds of millions of rows, and just testing various scenarios.
With concurrent selects. It's really important, right? That was your tip last
time. It depends. You might have only single session experiments and already understand a lot. If you use buffers, you see IO, and that's it. But if you need to check the behavior of the buffer pool of log manager, in this case, of course, you need full-fledged benchmarking multi-session experiments, and you need to be alone on that machine. But we had also an episode about experimenting and that benchmarking, I guess, right? If we did, we should repeat it probably. So here I see value in both approaches, just different value. Right.
Wonderful. Was there anything else you wanted to make sure we talked about?
I guess that's it. It's not all, far from being old, far from being polished, but I encourage everyone to think about their particular case with experiments. As usual, my usual recommendation: analyze with experiments. I don't call them benchmarks because explain, analyze buffers, it's also like performance related experiment. You can check plans, but it doesn't feel like benchmark, right? But just from this single thing, you can do many good optimizations. Right? So experimenting is the key for understanding your particular case. Yeah. I hope we highlighted directions of analysis, right? This is probably the main value of this episode. Okay, if you liked it, please like, subscribe, and share. I'm talking to our listeners.
Oh, I thought you were talking to me. Thanks so much, Nikolai.
I've noticed when you upload to YouTube, you don't like. I usually fix it myself, and I like our video because, yeah. Okay, thank you so much.
Take care. Bye.
Bye.